Welcome to session 11 of Fluid Mechanics Module 2. My dear students, so far we have covered the fluid characteristics, hydrostatic pressure, pressure on a plane surface, curved surface, and today we are going to a new system where the fluid is not static. So far the velocity was 0, now it is going to be moving. We would like to know what is its velocity, what is the acceleration, what is displacement and other things. So, welcome to session 11 once again. This part we are going to cover the fundamentals of fluid flow, which is called kinematics. The kinematics name is derived, it is mass independent. It means we are not bothered how the liquid is moving. We are only bothered to know its velocity, its acceleration, its displacement, etc. So, the learning outcome, the student will be able to describe the flow classification, apply principles of kinematics and hydrodynamics for practical applications, basic conservation law of mass, which is also called as continuity equation. So, mind it, my dear students, we are going to cover this portion. I will show in the board. The kinematics, the velocity is not 0. The fluid or the gas or the liquid is moving, it is not stationary. We are worried about its displacement, how fast it is going, how slow it is going. We are worried about its velocity. We are interested to know the acceleration of the fluid particle. We are also interested to know what is exactly conservation of mass, which I showed in the slide as continuity equation. Is it okay? Next one, we would like to know what are the different types of flow. I will describe one by one in my slide. What is the stream function? What is the velocity potential? Together these two forms a flow net. So, how the flow net is applied to hydraulics. So, these are the things we are going to cover. Let us start. Before I start, as I normally show the animation, you can see a bluff body is there. It could be like a duster, and the flow is taking place through this, or you can say it is a aeroplane and it is going this way. We would like to know how the pattern is changing. You can see the first one here, how it is called wake portion. This is the separation portion and this is the way it is going. You may be thinking it may be like a chimney, and how the air flows, the smoke goes like that. At the same time, we can see here a cooling tower of a thermal station like our Raichur, or it could be a Korba or any thermal power station, where the smoke is coming or the flow is going of the gases this way. The ribbon shows the streamlines. Very interestingly, a car is on the road and it is moving with some velocity. The ribbons you can see, it is a streamline. So, we would like to know how the velocity along the path of the car. And the most important, you can see a animation, it is a turbine. It is a turbine in which the entry is taking place and the water is moving, power is being generated, the fluid particles are under rotation. So, definitely there are different types of examples in which we can see a fluid particle moves. Fluid I always mean water as well as the gases. So, let us see our journey how it goes. Fluid kinematics, as the definition says, I will read the statement. The fluid kinematics deals with the description of the motion of the fluid without reference to the force. You might have heard there is a famous formula, F is equal to m into A. F is equal to m into A, where m stands for the mass and A stands for acceleration. So, we are not bothered about the force which is causing this motion. We are only bothered about its velocity, acceleration, displacement. Is it okay? So, this is what actually we say fluid kinematics. Come back to the slide. Without reference to the force causing the motion. Thus, it is emphasized to know how the fluid flows and how to describe the fluid motion. How to describe it. This concept helps us to simplify the complex nature of a real fluid flow. you know the flow around a body or in a system, in a turbo machinery or in a canal or in a river, it is very complex, or even sea movement also is a complex. We would like to know how to describe this fluid motion. Okay? When a fluid is in motion, individual particles in the fluid move at different velocities. Moreover, at different instants, fluid particles change their positions. In order to analyze the flow behavior, a function of space and time we follow. You may be thinking how to describe the fluid particle motion. If you take gases, all the number of particles are around. So, definitely we need to know how to describe the fluid motion. There are two approaches in the fluid mechanics we follow. One is the Lagrangian approach and other is Eulerian approach. We are going to describe that now. So, the Lagrangian approach is called system approach, describes a defined mass, position, velocity, acceleration, pressure, temperature, etc. as a function of time. I repeat again, in the Lagrangian motion we are looking to the defined mass. That mass could be say 10 particles, that mass could be say 1 lakh particles, how they move around. It means we are going to track only some few particles. For example, if there is a migrating bird, I would like to track those migrating bird how it is going along. That is called Lagrangian approach, in which we are going to trace some particles and how they move with time. Is it okay? I will describe further, do not worry. Let us see the Eulerian approach. It describes the flow field. Flow field means the velocity, acceleration, pressure, temperature, all other things as a function of position and time. We are going to see what is happening in a particular location. We are going to see what is happening in say this box, or maybe say if within this duster what is happening. I would like to know what is the velocity, what is the acceleration, pressure, temperature of all the particles who are in moving along this box or crossing this box, etc. So, these are the two approach. In one case we are going to fix the number of particles, in other case we are going to fix the boundary. So, Eulerian approach is one and the Lagrangian approach is one. Lagrangian approach you can always remember, it is one by one particle wise, which means you will take 10 particle, 1 lakh particle, 10,000 particle, etc. In the Eulerian we are not fixing the number of particles. I repeat, in the Eulerian approach we are not fixing the number of particle, but we fix the domain, maybe within this room, maybe within this duster, right. That is what actually, and whatever number of particles are coming here inside, that we are going to count how it is going to change velocity, acceleration, pressure, temperature within this boundary. Is it okay? Now, let us go further. Say if we are going to study water flowing in a pipeline, so which approach would you use? Definitely pipeline is a fixed domain, maybe some this point to that point. So, answer should be the Eulerian approach. So, Eulerian approach is very good for the pipe flow. Now, let us describe the Lagrangian description in our way. In the Lagrangian approach, a fluid particle of fixed mass, as I mentioned, some number of particles, and we follow the fluid particle. Example, in a classroom we have 60 students, and in that say if I take roll number 1 to 10, how the students are being tracked from the home to the classroom, again back home or somewhere else, I am talking about that only with time. Definitely that is a Lagrangian approach. Okay. Suppose if I talk about a classroom, how the students are behaving within the classroom, that is actually the Eulerian approach. I will show you the small animation. You can see in the Lagrangian approach a fluid particle of fixed mass is selected. We follow the fluid particle during the course of motion with time. We follow the fluid particles some bundle during the course of motion with time. Let us see how it goes. You can see here you can see here the fluid particles here coming to track the fluid particles of definite mass. Can you see that movement? It means I am interested only in this 4 particle. Again repeat, you can see these 4 particles, how they move along. What is their velocity, what is their temperature, what is their acceleration, what is their displacement. I am only interested in these 4, maybe 40, maybe 40,000, etc. I hope the concept is clear. The fluid particles may change their shape, size and state as they move. As mass of the fluid particle remains constant throughout the motion, the basic laws of mechanics can be applied. The task of following large number of fluid particle is quite difficult, but nowadays with supercomputers, maybe 1 lakh particle, 10 lakh particle, billion particles, definitely we can do, but it is time consuming and it is computer space consuming. Okay, let us see the next one. Eulerian approach. In this case, as I mentioned very clearly, within a region we are going to describe. I am going to take definite mass, maybe this room, maybe say this duster, exactly. So in the Eulerian method, a finite region through which fluid flows in and out is used. It means I will see how many particles are entering here and how many are leaving within the system, whether they are absorbed, whether they are coming fully out, whether they are going to go this way or this way, anyway, okay, that I need to study. So in the Eulerian method, a finite region through which fluid flows in and out is used. Here we do not keep track position and velocity of fluid particles of definite mass, but within the region the field variables are continuous function. Nowadays, for example, if you take pressure, it will be function of x, y, z and time. I would like to know all the particles within this duster, how they are doing with respect to time, but my domain is fixed. So that is called Eulerian description. It could be a pipeline, a portion of a pipeline, or it could be you can say a piston in a carburetor of an engine, or it could be a submarine, or it could be any fixed body or a fixed volume of mass over which we would like to see what is happening, the time history for its pressure, its velocity, its displacement and time. So hopefully I am able to give you the concept. What is the Lagrangian approach? Tracking of some particle. What is the Eulerian approach? Fixed volume approach. Is it okay? Let us go next one. Now I will try to do this part, which is called types of flow. Types of flow I would like to know. For example, somebody comes and he is not knowing about the fluid mechanics. He would like to say, sir, can you tell what kind of flow it is? Then how to describe? To describe types of flow, we will start with a time domain, we call it study. If I am standing still, it is a study. My movement is not there with time. But suppose if I keep on moving here and there, it is called unsteady. So my dear students, study and unsteady refers to the variation of flow characteristics with respect to time. Again, steady and unsteady totally is based on with respect to time. If the flow characteristics are not changing with time, you may be thinking, sir, what is this flow characteristics? Think, this is a system. Okay, at this particular point, say this point where I am mentioning, the velocity is, say example, 1 meter per second. You come after 1 hour and again measure the velocity here, same position, again it is 1 meter per second. Suppose you come tomorrow and see the same position, the velocity is 1 meter per second. This is called steady flow. Is it okay? So any characteristics which could be pressure, it could be velocity, it could be temperature or even concentration. It is changing with time, it is called unsteady. It is not changing with time, we call it steady. Is it okay? Now let us take one more definition. We have very nice name, uniform and non-uniform. Okay, if you go to a school, they have a uniform system. What do you mean by that? All the boys and girls, the students are wearing a one particular color, that is called uniform. Everywhere it is same, right? But suppose you go to any college or any say theatre, in that all the people who are wearing different colors, correct? That is called non-uniform, right? So the uniformity means the flow characteristics not changing with space. You may be thinking, what is this? I will show you the example. Say this is a bed of a river, okay, and this is my depth. Here to here depth 1 meter, here to here again 1 meter, everywhere it is 1 meter. So I am marching with space, maybe 100 meter, maybe 100 kilometer, maybe 2 kilometer, whatever. Everywhere depth is same, everywhere velocity is same, everywhere acceleration says 0. So definitely we can say it's a uniform flow. So uniform, non-uniform relates to the space x, y, z, marching in the space. Steady and unsteady relates to time. Let us take one example. Again same, this is the bed of a river and this is the depth. You can see depth here is say 1 meter and here it is reducing. So it is changing with space. It's a non-uniform, but at the same place the value can remain same. Example, here it's 1 meter and here say it is 0.5 meter. Say time now, say 3:5. Again you see at 3:45, again same 1 meter and 0.5 meter. Next day 1 meter, 0.5 meter. It is a non-uniform steady flow. I repeat, it is going to be the same for all the time, but it is different at different locations. That is called non-uniform steady flow. Is it okay? So definitely these two definitions based on the steady, unsteady with time, uniform, non-uniform with space is very much important. Let us take one more definition. Yeah, the name is very interesting, laminar flows. The flow structure is characterized, I will read the slide. Flow structure is characterized by smooth motion in lamina or layers. There is no macroscopic mixing of adjacent fluid layers. A thin filament of dye injected into a laminar flow appears as a single line. For example, I take a dye, say KMnO4, potassium permanganate, and inject in a pipeline. You can see the line will move exactly the same. There is no mixing of these layers in each other. We call it lined movement or laminar movement, like a military movement. It's a totally defined, okay. And we have the other part of it which is called turbulent flow, in which lot of mixing will take place. Again you will be thinking, sir, we are not able to follow, can you give an example? I will give a very good example. When you go to a cinema or a drama, you take the tickets, you are going in a one line, one after the other, you pay, take the tickets and go inside the hall, correct? It's a laminar flow, one after another. We are not changing or intermixing in the system. It's a line flow or a military flow, in which we can define very well the velocity, very well the acceleration, and very well the displacement also. So laminar flow. But when you come out of the cinema theater, what you do? You sometimes you push somebody, somebody is pushing you. That's a lot of mixing is there. Your motion is not like when you have taken the ticket. So it's a random motion. Okay, lot of loss is there. Sometimes you also shout, hey, who is pushing me, right? So that mixing is very high. The violence of motion is the turbulent flow. Laminar flow is a orderly motion, or you can say it's a military motion, right? So it is very well defined in line. They go one by one, they go by layers. You may be thinking, what is this layer? It's a layer in a pipeline. This velocity is say 0.5. This may be 0.4, this may be 0.2. So they move with the same velocity. Here also, there is no movement of, no mixing of layers. Okay. Let us see the turbulence. I think as I mentioned, the characterized by, you can read the slide, characterized by random 3-dimensional motion of fluid particle. It means the velocity is not regular. You can see here velocity is continuously same. There is no fluctuation here, right? And in this case you can see strong mixing of fluid particles from the adjacent layer, from this point to this point, this point to this point, they cross each other. So what is a turbulent flow? Turbulent flow is a random flow. Turbulent flow is a mixed flow. Turbulent flow is basically a unsteady flow, or it could be a steady turbulent flow also. So there is no universal relationship exists between stress field and the mean velocity field. So mind it well, the laminar flow is well defined. Laminar flow is a orderly motion. Turbulent flow is a episodal, random, and it mixes very fast, and you can see there is a mean velocity u bar and there is a fluctuating component with respect to time. So, in the laminar flow this value will be 0, you will get same value u bar everywhere, same velocity, okay. And in case of turbulent flow you can see it is fluctuating, with respect to the mean value. This is the mean value, say 1 meter per second, fluctuation can be of the order of 10 centimeter per second or 0.1 or 10% or 20%. Is it okay? So, one thing I made you clear, the laminar flow and turbulent flow are basically the way how the fluid particles are following their path. If they are following a fixed path, we say it is a laminar flow, but if they are not following the fixed path, they are randomly moving here and there, mixing with others, dashing other fluid particles, it is called turbulent flow. So, my dear friends, my dear students, the losses will be more in the turbulent flow. Turbulent mixing is very dangerous, it's losing the energy there. Let us take one more method. We are describing types of flow. I already told steady, unsteady, turbulent, uniform, non-uniform, laminar. I go to one more term called one dimensional flow, two dimensional flow, three dimensional flow. I know as my student you will be able to answer, sir, one dimensional is only one dimensional, two dimensional is two dimensional, and three dimensional is three dimensional. Your answer is perfectly alright, because one dimensional flow means, I will just go to next one. One dimensional flow means if the flow parameters such as velocity, pressure, depth, temperature at a given instant of time only vary in one direction and not cross the each other. We can see here this velocity which I showed for a ideal machine flow is constant everywhere, okay. So, it is only u is in the direction of x only, correct. You can see it is only in the x direction. So, it is one dimensional flow. It means I am able to define the fluid flow or fluid characteristics with only one dimension. U is a function of x, like this. A train which is going on the straight line, we can say u is a function of x. It is a one dimensional flow, okay. Normally it is true only for ideal flow, as the slide indicates very clearly in a pipe, but real fluid we will see next one. Two dimensional flow. Now, u is a function of x and y, or v is a function of x and z, or u is a function of y and z. It means we need two coordinates to define. Earlier my formula was u is equal to say kx. Now, formula will be u is equal to kxy. It means I need two coordinates to define the flow. That could be velocity, that could be pressure, that could be temperature, or anything. So, definitely this is very important. We are able to describe the flow with two dimension, okay. So, two dimensional flow are very common. They are real fluids, and you can see the velocity is varying in this particular slide in two direction. One is x direction and other is y direction. Is it okay? Now, we can see in the VR also the two dimensional flow is obtained, okay. So, it could be two dimensional. Now, we go to the next one. Three dimensional. Now, we can see the velocity is a function of x, y and z. So, as you mentioned very clearly, or as you thought clearly, one dimensional flow, the characteristics can be defined by one dimension. Two dimensional flow, characteristics can be defined by two dimensions, and if the characteristics can be defined by three dimension, it is called three dimensional flow. Is it okay? So, we go to the next thing. Now, before I continue, we have covered so many definitions. Now, we would like to go to a very important concept called streamline, streak line and path line, okay. Streamlines, in analyzing the fluid flow, it is very useful to visualize the flow pattern. I would like to visualize the flow pattern. This can be done by drawing lines joining points of equal velocity. For example, say this is okay, I will take this example. example, this is a cloth, and it's got this velocity is same, and here also velocity is same, and here also velocity is same. So, I will join the point here, here and here, that is become a streamline. It is the point of equal velocity, points of equal velocity we call streamline. We draw tangent, we get everywhere the velocity. Is it okay? So, in analyzing the fluid flow, this streamline concept is very important. It is going to help us to visualize the flow patterns. It is going to help us to visualize the seepage value. It is also going to help us to know the curvature of flow, etc., etc. Okay? So, streamline will continue. A streamline is a point, is a curve that everywhere tangent to the instantaneous will give the local velocity vector. For example, if my hand is the streamline, if I draw tangent 1 meter per second, tangent 1 meter per second, tangent 1 meter per second, everywhere I am drawing tangent, it is showing me the same value. Okay? It is actually instantaneous at that time equal to 0 second, 1 second, 2 second. So, it will vary definitely. So, a streamline is a curve that is everywhere tangent to the instantaneous local vector. Now, consider an arc length must be parallel to the local velocity. Local velocity V has got 3 components: U along the x axis, V along the y axis, and W along the z axis, which I showed here in the V vector is equal to Ui plus Vj plus Wk. Now, the streamline equation is dr by V is equal to dx by U, dy by V and dz by W. It means displacement in x direction is responsible velocity in x direction. Displacement in y direction is responsible because of the component of velocity in y direction, and displacement in z direction is responsible in the velocity in z direction. I repeat, the dx by U, displacement in x direction proportional to the velocity in x direction, displacement in y direction dy, component is velocity component is V, displacement in z direction velocity component is W. So, very simple equation for streamline is dx by U, dy by V and dz by W. This is a very important point. Geometric arguments results in the equation, which is, you can see the velocity vector V with a position vector dr is equal to dxi plus dyj plus dzk. So, streamline is a curve that is everywhere tangent to the instantaneous local velocity vector. What exactly it means? If you draw a tangent here in the cursor 1 meter per second, again draw here 1 meter per second, again 1 meter per second, wherever this line is there, the point of equal velocity, point of equal velocity, that is streamline. In the streamline, you can see a car is shown in which the ribbons are drawn. You can see the points of equal velocity. It is bending also. You can see a ribbon on an aeroplane exactly like that I have shown, and the ribbons are showing points of equal velocity. So, these are very important, and one more thing is streamlines cannot cross each other. Why? Suppose if two streamlines cross each other, what will happen at the point of intersection? What will happen? It will, if you draw a tangent, I told no, 1 meter per second, 1 meter per second, 1 meter per second. Everywhere the velocity should be same. But if they cross each other, the velocity at the crossing point will be 2. One will be 1 and one will be 2. That cannot happen. Is it okay? The streamlines cannot cross each other. If they cross each other, that means the characteristics has got a dual value. So, that is the reason streamlines are very important in drawing the pattern of flow over a aeroplane, over a weir, over a dam, over a car, or in a pipeline also. So, any particle of fluid starting on one streamline will stay on that same streamline throughout the field. So, the particle will remain there only. Now, is it okay? Let us see further. Next, we will define a very interesting name called path line. Okay. Again, as my student, I know you know very well, path line means path traced by a single particle. I repeat, path traced by a single particle. For example, you as a student, you start from your home, you are sleeping, your velocity is 0. You got up, some velocity, all activity, going to the college, some velocity again changing, come to the class, you are sitting, again velocity is 0. It means the path line is basically the path traced by a fluid single particle, maybe a single individual at every instant of time. That is called path line. So now I will read the slide. A path line is the actual path travelled by an individual fluid particle over some time period, same as the fluid particles like position vector. I would like to know where it is going. A one particle, for example, if this room has got a air and air particle is say coming here, say, so this is a particle, okay, it's here, say velocity is 5, then it's coming 2, then it's coming 3, then it's coming 2, 4, 3. It means till it leaves the room. Definitely I am tracking the path of a single particle along the time, how it is going. Its velocity will change with respect to time, its pressure will change with respect to time, its temperature will also change with respect to time. Is it okay? So that is actually the path line. Path line is the path traversed by an individual particle. Is it okay? Next we come to the streak line. A streak line is the locus of fluid particles that have passed sequentially through a prescribed point in the flow. A streak line is the locus of fluid particles. For example, if I take this duster as a chimney, okay, and the top you assume this is the chimney, I assume that there is a line. Whatever particles are passing at instant of time, say time t equal to 0, say 10 particles are crossing this line, I will simply trace those 10 particles how they are going. Okay, a streak line is the locus of fluid particles that have passed sequentially through a prescribed point in the flow. This is very useful in the AC. This is very useful in the ventilation. I would like to know how many air particles have entered my room, say 1 lakh. How this 1 lakh particles are moving around the room and out, that I am interested. That is actually a streak line. It is easy to generate dye in a water flow or a smoke in a air flow, right? You can see air in a chimney, how it is going. You simply trace where it is going. That is your streak line, right? So we have described 3 important things: streak line, path line, and streak line and streamline. So streamline is a line in which if you draw a tangent, you get same velocity vector. 2 streamlines cannot cross each other, number 1. Number 2, path line. Path line is the path traversed by a single fluid particle. Single fluid particle. I am not talking about many, only one. With respect to time, what is its position vector? Streak line is the locus of a fluid particle that have passed sequentially through a prescribed point, say my hand. How many particles have passed? Say this point. I may be interested in that, in this length only, say 10 particles. Say how this 10 is going around that, that is your streak line. So these are the 3 important definitions which I have given you: streak line, path line, and streamline. Now we come to a very important concept called stream tube. You may be thinking, what is this tube? You know only tube in a tire. Okay, a stream tube is made of streamlines. The walls are made of streamline. For example, if you take this pen cap, it's a tube you can see here. So all these are having a streamline. All the boundaries are associated with a streamline having a different velocity. So if I define the boundary of many streamlines, note my point. If I define a boundary of many streamlines, that will form a stream tube. For example, if this is the thing, I take one streamline is here, one is here, one is here, all along the boundary if I define, definitely that is the way the flow takes place. If you take water, if water is flowing through this pipe can be taken as a stream tube. Exactly correct. Why? Because on the boundary some velocity will be there, at the center some velocity is there, so like that it is going on. So the walls of a stream tube are made of streamlines. Fluid cannot flow across a streamline, hence fluid cannot cross a stream tube wall. Definitely if it is a pipe, the flow will not come out from anywhere unless it is punctured. Okay. So the stream tube can often be reviewed as a solid walled pipe. It means if there is a pipe here, we would like to know that pipe is nothing but the streamline. A stream tube is not a pipe. It differs in unsteady flow. If it is a steady flow, it will remain same always. But if it is an unsteady flow, the stream tube is keep on changing every instant of time. So a stream tube is a very important concept which is made of streamlines only, but it will change every instant of time. For an unsteady flow, it will remain same for steady flow, right. Now let us see how it looks. You can see I have shown a path line, a path traced by a single particle. Can you see here? This point is the stream tube. One streamline here, one streamline here, one streamline here, and one streamline here. Definitely this is very important, because with this we can have the flow description. This point B, you can see it is following B, 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 B. Everywhere it is not changing the path. Exactly, you may be thinking a laminar flow. You are very correct. It is along the laminar flow. Takes next point, say C. This will carry on like this. It is also a single particle. So this is a path line traced by a single particle, right. Now let us see the streak line. Streak line, the fluid particles that have gone through a fixed station. For example, if I take this particular location, a particle say was here earlier, next instant it has gone here, next instant it has gone here, it is gone here. It is a streak line, because this fellow was here, this particle has crossed. So that is very important. The fluid particles that have gone through a fixed station or point at some instant of time, the position of all these particles are marked and a line is drawn through them. So that is called streak line. The streak line is a fluid particle. Now you can see a small animation is there on a streak line on an aerofoil. This is the aerofoil, exactly like a wings of a bird, or it could be a wings of a aeroplane. So you can see the streak line is here, how it is going. Exactly you can see the path. Here also you can see how the streak line is going in an aerofoil. Is it okay? Now we will come to a very interesting definition. You will be thinking, so far I have defined so many. Let me come back. Steady, unsteady, time domain, steady, no change of characteristics with time, steady, unsteady, uniform, non-uniform with reference to space, maybe depth, maybe velocity, etc. Then we talked about laminar flow, turbulent flow, orderly motion, laminar flow, mixing motion or violence of motion, turbulent flow. Then we have talked about the path line, streamline and streak line, which is nothing but the streamline is whichever point you draw a tangent, velocity is same, we say streamline. Path traversed by a single particle is a path line, and number of particles crossing a particular location, if you trace how they are going, that is actually streak line. So these are the important definitions we have given so far, and we come to one more important way of describing the flow, which is very common in the practical application. The name is irrotational flow and rotational flow. You may be thinking, what is there, sir? Same way. Irrotational means it is not rotating at all. It is not rotating at all. Rotational means it is rotating in the system. You are very correct, my dear student. If a fluid particle does not rotate about its mass center, it is called irrotational flow. I repeat, a fluid particle does not rotate about its mass center, it is called irrotational flow. I will show you the example. You can see in this case one fluid particle is coming, it is here with the same phase, again here with the same phase, here also the same phase, and here also same phase. So definitely it is not at all rotating. We can say the fluid particle is not rotating. Now what is a rotational flow? Rotational flow is a flow in which the fluid particle rotates about its mass center. You can see if this is a fluid particle, this chalk, irrotational is same, it is going same way in the system. Rotational, it is going and rotating also. Can you see that? It is rotating also. You can see this in the slide also very clearly. This particle is turned by some degree, maybe some 30 degree, then this side 90 degree, again it is going, it is fully opposite now, 180 degree. So fluid particles are rotating. Now you may be thinking why we are talking about such a classification, where this is important, right? If you see any stationary system, the wind is coming, wind is more or less, it is in the same flow, the particles are not rotating, it is coming same way, okay, and then it is going, we can say it is a irrotational motion. But the moment it touches a bluff body like a car or a building, it is going to turn like this. I can show you, I showed you in the animation also, same thing I will repeat and show what exactly I mean. If you are coming here, I will show here, yeah, you can see here, in this case the first one on the left side and the top, it is having rotational flow, right, continuously the particles are moving around, that is rotational flow. Before that it is going straight, it is going fully straight, we say it is a irrotational flow, there is no rotation at all. So now we are more interested to know what is this irrotational flow and what is the rotational flow in terms of application. Now I will remind you a small example for you. If you go to a river, observe its banks, the particles are moving straight, we can say straight flow, or we can say the fluid is not rotating, right. But there are centers in the river where you can see it will be moving around, that is called free vortex, we call free vortex, and highest velocity is at the center, okay, you can see like that. Suppose you do brush also, in the sink also, suppose you remove, the velocity will be higher at the center, okay, and less and less outside, exactly like this. Here velocity is 1, 2, 3, they are all moving like this, we say V is equal to K by R, lesser the radius, higher the velocity, okay. So lesser the radius, higher the velocity, this is called free vortex. In this case all the fluid particle, whether it is a river, whether it is a wash basin or whatever it is, they are in the rotational motion, and that too we call it free vortex, we call it free vortex. Then you may be thinking, if I am talking about the free vortex, whether there is a forced vortex, answer is yes. In the forced vortex we are going to be like this. In the forced vortex the velocity will change, forced vortex velocity will change with reference to directly proportional to distance. So higher the distance, velocity will be more. You can see the fan blade higher in the other side, center it is less, car wheels at the center velocity is less, outer side velocity is more. In a mixie same thing. So these things are called forced vortex and free vortex, they are under rotational motion, the fluid particles are moving around its mass center, this is called rotational motion. Irrotational is not at all moving, it is a straight line motion, right. So irrotational flow and rotational flow, I have talked about forced vortex and free vortex with the example. Is it okay? Let us go to the next slide. We have one more concept called flow net. Flow net is a graphical representation of two-dimensional irrotational flow. Flow net is a graphical representation of a two-dimensional rotational flow. No doubt I have not covered the psi line and phi line, which I will be taking tomorrow, but today I would like to cover this flow net concept. It is basically a net, like you have fish net, no, exactly, one line is psi line and perpendicular is a phi line, exactly like this, psi lines and phi lines. So, you can say on the x axis it is the stream function or it is a velocity potential. So, if you take the grid of that, it becomes a basically a flow net. Why this flow net is required? Whether this flow net is a straight line, whether it is a curve, those things are very important, because we are going to use this under the seepage of the dams. We are going to see how the flow is taking place over the weirs. So, the flow net is a graphical representation of a two-dimensional irrotational flow consisting of streamlines on the x axis and phi lines on the y axis. You can see in the slide also, I need not worry about it. You can see it is a rectangular and it could be even curve also. Phi lines and psi lines, they are always perpendicular to each other. Phi lines and psi lines are always perpendicular to each other. Question arises where they are being used. Okay, they are being used in the determination of the leakage, they are being used to calculate seepage, they are being used to calculate hydrostatic pressure. These are their different uses are there. So, there are different methods are there that I will explain. There could be current analogy method, phi psi method, direct graphical representation method, all those, these are the methods we are going to use. Now, let us come to one more important point, we will call mass conservation. Mass conservation is a thing, we say matter is conserved. It means whatever the matter is coming in a system, same is going out. Exactly, it is like a Kirchhoff's law. Whatever current comes, it has to go out. So, if in a river system or if in a room system, if 100 particles are coming, 100 should go out. That is the balance we have to see. We say the density into area into velocity, it should be same. It means density of the liquid into area at the one at area. I will show you a small example. Here you can see a small pipeline, say this one, assuming that flow here is 30 kg per second. In this case also 30 kg per second. We say mass is conserved. It means whatever rho a v is there, that is the mass per unit time, that is a conserved. No doubt, whatever may be the density, what is the area, if area is more, velocity will be less. If area is less, velocity will be more. So, this is way it is going to balance each other. We say conservation of mass, we say it is a continuity equation. I have written the formula also, we will discuss this later in tomorrow's class, how the conservation is done. Dou rho u by dou t, dou rho u by dou x, dou rho u by dou v, dou I, dou rho u w by dou z. So, it is a 3-dimensional continuity equation which we are going to use in our numerical. So, it is a conservation of mass. Sometimes people say q is equal to a1 v1 equal to a2 v2, but the density is the same. If it is a liquid, we say compressible, rho and rho gets cancelled, we get a1 v1 equal to a2 v2. It means if this is 5, this is going to be 4, and if this is 4, this is going to be 5. So, the overall product is 20, that remains the same. Overall product is 30, which I am showing here, it is going to be same. So, higher the area, velocity will be less, lower the area, velocity will be very high. So, this is what the conservation equation we discuss. Is it okay? Next, we are going to talk about the velocity components and acceleration. Let me again brief you. The x component of velocity is u, y component of velocity is v, z component of velocity is w. If I make the acceleration vector as ax I, ay j, az k, the ax is given by dou u by dou t, that is called local derivative, and this is convective acceleration term, which is u du by dx plus v du by dy and w du by dz. Ay is dv by dt, dou v by dou t plus u dv by dx, v dv by dy and w dv by dou z. My dear students, make a note, ax will carry u everywhere, ay will carry v everywhere on the top, and az will carry w everywhere. So, take care, these formulas are important. We are going to solve problems on this based on the x component, y component, z component, its velocity vector, its acceleration vector on this one. So, based on these two concepts, which is a local derivative dou u by dou t or dou v by dou t or dou w by dou t, and these are all called convective acceleration terms, which are going to be u du by dx or v du by dy and w du by dz. So, mind it well, it is a partial derivative. If I take dou u by dou x, what is the meaning of that? The u component of the velocity is partially differentiated with respect to x. It means I will take only x as a variable for u and all others will remain constant. Repeat, dou u by dou x means the partial derivative of the u component of velocity with respect to x distance. In that case, all other variable y, z, t, they are all constant. We are not going to differentiate them. We treat them as a constant. We will only differentiate dou u by dou x, means u with respect to x only as a variable. That is why the name has come partial derivative. Is it okay? So, these things we are going to see tomorrow, and I thank all my students for their kind attention. Today we have discussed so many definitions. We have some more definitions tomorrow, and no doubt we are going to solve the problems tomorrow onwards. So, thank you.